Welcome to our explainer. Today, we're going to tackle a fascinating and, frankly, incredibly high-stakes problem, securing our most critical infrastructure. We're talking about the electrical grid, water treatment facilities, and, yep, even nuclear power plants. So how do you protect these vital systems in a world of constant cyber threats? Let's dive in. So let's just start with a question that should make you a little nervous. How do you connect a modern working nuclear power plant to the internet? Because you have to, right? Corporate HQ, they need that data for efficiency, for maintenance, for planning. But the risks, well, they're just astronomical. The short answer is, of course, you do it very, very carefully. But carefully in this context means something totally different. It means you have to face this fundamental conflict right at the heart of the system. Because let's be real, the old security playbooks, they just don't cut it when the stakes are this high. And that brings us right to the core of the issue. It's this huge conflict between two things that seem to completely oppose each other: the need for constant data and the need for absolute, unbreakable security. See, on one hand, you've got the corporate side of things. They are demanding real-time data streaming from the plant. It's absolutely essential for them to optimize operations and predict when a piece of machinery might fail. But on the other hand, you've got the plant itself, this massive industrial control system that, for very good safety reasons, was designed to be completely cut off or air-gapped from the outside world. The second you connect it to an external network, you introduce a massive, massive risk. Now, what's really fascinating here is how this whole situation completely flips security priorities on their head. In your typical corporate IT world, confidentiality, keeping information secret, is king. But inside a plant control system, the #1 priority, above all else, is availability. That system has to stay online and working, no matter what. Integrity, making sure the data is accurate, that's pretty important to both. But for the plant, just keeping the lights on is way more critical than keeping its data secret. So what was the traditional fix for this? Well, the go-to answer in network security for decades has always been the firewall. But in an environment this sensitive, the good old firewall has some pretty serious problems. A common setup is something called a demilitarized zone, or a DMZ. The best way to think about it is like a guarded lobby between a public street and a super secure building. Data from the plant goes into this DMZ, and then corporate users can access it from there. The firewalls, they're the guards, trying to stop anyone from the outside from getting directly into the plant network. Sounds pretty reasonable, doesn't it? Well, here's the problem. Firewalls are fundamentally flawed for this kind of job. They depend on these incredibly complex sets of rules that are just so easy for a person to mess up. They need constant, expensive maintenance. And the real kicker? They can't protect against what we call zero-day exploits, these brand new attacks that no one has ever seen before. So the most important point is this: a firewall is a piece of software. And any piece of software, no matter how perfectly it's written, can be hacked. Period. So if a software guard can be tricked, what's the alternative? It's not about building better software. No, it's a completely different way of thinking. It's an elegant and incredibly powerful piece of hardware called the data diode. A data diode is, well, it's exactly what it sounds like. It is a network security device that forces data to flow in only one direction. Information can go out, but absolutely nothing can come back in. And that's not just a rule or a setting you can change. It is guaranteed by the laws of physics. And this really shows the difference perfectly. A firewall is like a bouncer with a long list. It's complicated, it has to make judgment calls, and it can definitely be fooled or just overwhelmed. A data diode, on the other hand, is like a physical one-way turnstile you'd see at a stadium exit. You can go out, but you simply cannot go back in through it. It's simple. It's unchangeable. Its security is baked into the hardware, not the software. So how does this thing actually work? Well, the most common type is an optical diode. So inside, you've got a fiber optic cable. On one end, there's a laser that sends data as little pulses of light. On the other end, there's a detector that receives that light. But here's the key. That light detector is physically incapable of creating and sending light back. It can only receive. It is a one-way communication channel, guaranteed by physics. You can't hack it to send data the wrong way. It's just not possible. Okay, so a one-way street sounds perfectly secure. Awesome. But it also sounds completely impractical, right? I mean, how can a one-way device possibly work in a world that is built on two-way communication? This is the million-dollar question. Almost all of the internet, including the standard TCP/IP protocol that everything runs on, requires a two-way handshake. You know how it works. Your computer sends a request, the server says, got it, and then sends the data. If you just shove a one-way diode in the middle of that, the whole handshake breaks and the communication just fails. The solution, it turns out, is surprisingly clever. You basically trick the network using two special servers. So on the secure plant side, you have a source server that talks to the control system, and it performs that normal two-way handshake. Then, it carefully strips out only the data that needs to go out and sends just that across the data diode. On the other side, a destination server catches that data and then it rebuilds a completely new, separate, two-way session for the corporate users. The network thinks it has a perfect two-way connection, but the whole time, the diode is maintaining that physically enforced one-way barrier. Okay, so we've buttoned up the perimeter. It's secure. But what happens if the threat isn't coming from the outside? What if an attack starts inside the supposedly secure plant network? And this is a really big deal. Just imagine someone plugs an unauthorized 3G modem into a random computer on the plant network. Or worse, a malicious insider gets physical access. They could completely bypass that main data diode we just set up. This really shows that having one big gate at the front door isn't enough. You've got to think about protecting each and every critical system individually. And this is exactly where the technology is evolving. To fight back against these more complex threats, there's a whole new generation of data diodes coming out, and they are focused on a pretty radical idea, a hardware-only design. Just look at this quote from our source material describing a modern diode from a company called HackBook. No microcontroller, no CPU, no firmware. Think about that. That is huge. It means there is literally zero software running on the data path of the device itself. And no software means no vulnerabilities, no patches to worry about, and no remote attack surface. None. This table really makes the advantage crystal clear. Older diodes, they might still have some firmware or a little embedded controller, basically a tiny bit of software that could potentially become an attack vector. This hardware-only approach completely eliminates that risk. And notice the logging too. This new design uses a completely separate air-gapped port just for management. That means that configuring the device or checking its logs can't possibly interfere with the actual data path, which reduces the risk even more. So how do you actually build trust in a device like this? You design it with security baked in at every single level. This one uses a hardware-based whitelist, which means only pre-approved devices can even send data through it. All other traffic gets dropped at the most basic network layer. The user interface you use to set it up is physically isolated from the data path, and the whole thing comes in a tamper-evident box so you'll know if anyone has physically tried to mess with it. What this all leads to is a completely new way of thinking about security. It's about moving beyond just complex software defenses to something way more fundamental. It's about how we can build trust in a zero software world. At the end of the day, securing our most critical systems, it really all comes down to a balancing act. It's this trade-off between how much a solution costs and how complex it is versus the absolute rock-solid assurance it gives you. For something like a nuclear plant, where assurance is literally everything, a simple, physically enforced hardware solution offers a level of trust that complex software just can't touch. So, this leaves us with a pretty fascinating final thought. As our digital world gets more and more complex, with software vulnerabilities hiding around every corner, is it possible that the strongest shield we can build is actually the simplest piece of hardware, grounded in the unchangeable laws of physics?